So let's talk about additions to alkynes, and in this case we're going to draw a parallel back to alkenes. So when we added HX to an alkene, what did we get? Well, HX added and we got the halogen, the X, going onto one carbon and the hydrogen going to another carbon. The question was which was which? Well, to do this we had Markovnikov, and this is going to kind of follow the same idea. There's a reason I've intentionally drawn this as a terminal alkyne. When we do our first addition with HX, the way it works is that we have our halogen and we have our hydrogen. And the halogen here is going to attack the most substituted carbon. So if this was a symmetric one, really wouldn't be a good illustrative purpose. Now, they're also going to attack on opposite sides. So the first addition, instead of having 2x, we just had a 1x, would result in this alkene. So the H and the X are added opposite to each other. If we were to describe it, we would say they were trans to one another. And this is the first addition. But if we're good enough to add to the alkyne, we're also good enough to add to the alkene. So the second addition here is going to follow a very similar mechanism. Once again, we've got the X, our HX, and our hydrogen. We're going to get an attack on the carbon, and this will result in a second addition to the most substituted carbon. So this addition of HX to our alkyne, if we have two equivalents, will give us double addition. If we're only getting one equivalent, in principle, we can get a single addition with basically the X and the H being trans to one another. And this is a good way to generate what are called geminal halogens, two halogens added to the same carbon. Let's say you don't want to do that. Let's say you want to add halogens on opposite sides, the double, triple bond, how we do it. Well, let's talk about that next.